So this video is going to be a quick video on everything you need to know about exponential functions. So the first off, this is what we mean by an exponential function. When we talk about an exponential, we mean that we have some base number being raised to an exponent that is our variable. So as we input, we're going to be inputting into the exponent. Now, x could have some other things with it. So an example, this could be 3x plus 5 or x over 2 minus 8. Those are different types of transformations. But notice that in our base equation, our parent one here, we don't have anything with x. So what that really means is we're going to look at this through the scope that if there is something up here with x, we can rewrite it to make sure that x is by itself. And we'll look at an example of what I mean by that. But for now, we need to be able to identify what do a, b, and k do to our functions. So with exponential functions, we have two kind of options. You can have a growth graph or a decay. Growth typically looks like this. It starts out really flat and then it grows exponentially. So it starts out really flat and then it grows and it gets really steep. Decay is exactly the opposite. It starts really steep, but it is decaying exponentially, so it quickly flattens out. So this is our difference between growth and decay. So our function here can tell us a few different things. Our a term is really important. It's found on the front, and it's typically our initial value. So often when we're talking about exponential functions, we're talking about the value of a bank account, or we're talking about the value of a car, or interest, things like that. And so your a term, what you find in the front that's multiplied to your base, is that initial amount, whatever you're starting with. Because of that, if there's no vertical shift, which we're going to find out is our k value, then your a value is your y-intercept. The other big thing that a can do is that if your a term is negative, it actually reflects your graph vertically. And so what that could look like, both of these are our basics, so they have a positive a value. This is what we're used to seeing. But if that a value became negative, it would flip it over the x-axis. So we're going to go from, instead of going up exponentially, we're still going to grow exponentially, but instead we're going to go down. Same thing with the decay of a decay graph. We're still going to be flattening out, we're still decaying, but instead of starting up here in the positive world, we're going to start here in the negative. So these are actually our four kind of options that we have here. These are still both growth, these are still both decay. I know that because as I move to the right, both of these are getting steeper quicker, versus as I move to the right, both of these are flattening out. Going up to positive infinity versus negative infinity is just based on that a term. Is it positive or is it negative? The other option we have, I accidentally had that as b, should be k. The next one we want to look at, is our k value. The k value, as I mentioned earlier, is going to be that vertical stretch. And so what we mean by it being a vertical shift is that it can either move your graph up or it can move your graph down. The two key features that it moves is your y-intercept and your horizontal asymptote. So where your graphs flatten out, these are known as our horizontal asymptotes. And your k value would move those either up or down. And all of these, because they're basic ones, they're kind of flattening out close to zero. So if you don't have a k value, that means that it's really zero, and that's where your asymptote is going to be. But as you move your graph up or down, what you're doing is you're moving where is that asymptote. So what we can say from that is that our y-intercept is actually 0, a plus or minus k. So it's that initial amount plus your shift. And then your horizontal asymptote is actually basically just y equals k. No matter where you are, your horizontal asymptote is just going to be that k value. Okay. The last thing that we need to talk about is how does b affect growth and decay? So we have two different kind of worlds here. We're going to look at growth first. There's some things we need to know about growth. Growth happens when your v value is greater than 1. So multiplying anything by 1 consistently just keeps the value the same. But when your b value becomes larger than 1, well then as you raise it to an exponent, it's going to keep getting bigger and bigger and bigger, which means that you're going to multiply it by another number, which is going to get bigger and bigger and bigger and bigger and bigger. So having a b value greater than 1 is what causes you to have growth. The other thing we need to talk about with growth, as we've seen here, is that growth graphs get steeper. So they start with their horizontal asymptote on the left, and they go to positive or negative infinity on the right. What that looks like in terms of end behavior is that the left-hand side, which is always as x goes to negative infinity, y is going to go towards their horizontal asymptote. Versus on the right, so as x goes to positive infinity, their y is going to go to positive or negative infinity. And once again, that's just based on did you have a positive a or a negative a. So those are your growth graphs. Decay, on the other hand, similar, but most of the things are kind of switched just a little. Decay happens when your b value is less than 1, but also greater than 0. So if b is a negative number, it's not actually exponential. B must be between these two. These ones get flatter. So they start on the left really steep and they flatten out to their horizontal asymptote. So these ones start at positive or negative infinity and go to their horizontal asymptote. What that ends up meaning for their end behavior is that on the x side, as x goes to negative infinity, so on that left side, y is going to positive or negative infinity. So once again, the left-hand side, where they're going to positive infinity or negative infinity. And then on that right side, so as x goes to positive infinity, that's where your y value is going to your horizontal asymptote. So these are the quick basics. And once again, all of this is assuming that x is by itself. So if we look at a really basic problem just to get started, let's say y equals 3 times 1.2 x plus 5. So the first thing I'm going to notice is that my b value is 1.2. So b equals 1.2, which is greater than 1, so this is a growth graph. Because my a value is positive, I know that means I'm going to go towards positive infinity. So quick sketch, not even thinking about y-intercept or horizontal asymptote, I just know I'm starting flat, going up to the right-hand side. My y-intercept is always going to be that initial amount. So my initial amount was 3, and then whatever shift I have. So it then gets shifted up 5. So my y-intercept is actually going to be at 8 here. My horizontal asymptote is just my k value, and so I'd say my HA is at y equals 5. But in upper level, we don't always just want to say a horizontal asymptote. We want to look at that scope of end behavior. So we're going to say that on the left-hand side, our y is going to go towards that guy. And then the right-hand side, once again, because it's a positive a value, I know that we're going to go towards infinity. The last little bit here we got to talk about is the range. Once you can have your sketch, you can see the range a little bit more. So here we can see, talking about my range, is where my y values start. So if I'm coming down from the bottom, the very first place I'm going to see my y value is where my graph flattens out. And that's my horizontal asymptote. And then I know that my graph's going to keep going, and because of this arrow, and just because of the way the exponential works, it's going to keep going all the way up to infinity. And there we have it. Those are kind of the key parts. Now that I have this, I could draw a better sketch if I wanted. So my y-intercept's at 8. My horizontal asymptote is at 5, so a little bit beneath that. And then I know that I'm going to go here, go through that point, and then go up. So that would be a slightly more accurate sketch of my function here. Okay. I want to talk about this idea about range just in a little bit more detail while we have these sketches here. Let me erase some of this other stuff. Okay, so talking about the range really quickly, we notice that we're going to change the range between positive a's and negative a's. We just saw that with a positive a, our graphs start at a horizontal asymptote. And notice that it doesn't matter if it's growth or decay. As I'm coming up from the bottom, the first place I see my function is where it's flat, and that's my horizontal asymptote. If I come up from the bottom, the first place I see my function is where it's flat, which is the horizontal asymptote. Because a is positive, they're going to keep going up all the way to infinity. So your range for a positive a graph is just a horizontal asymptote up to infinity. Versus if your a was negative. So these were our negative a graphs. Notice as I come up from the bottom, I run into this arrow, which really means these were starting all the way down at negative infinity. Then where they stop is where it flattens out. It doesn't go above here. Where it stops is where it flattens out. It doesn't go above here. That flattening out is my horizontal asymptote. So this is how we could always write the range. Positive a is your horizontal asymptote up to infinity. Negative a is negative infinity up to your horizontal asymptote. So looking at this example we just hit, once again, notice that for x, there wasn't anything with it. So we were able to use all of those rules we just talked about. The question then becomes, well, what about if there is something with it? So let's just look at a very basic equation. Let's say that we had y equals 3 to the x plus 4. Well, if we actually hold off for a second and go to the side, we want to get rid of this plus 4. And so let's think about our exponent rules really quickly. Let's say that I had 2 squared times 2 to the 5th. We know that this would become 2 to the 2 plus 5, which is 2 to the 7th. This is the step that's really important. Notice I was able to rewrite these as one base that are being added. Well, we can also go backwards then. So if I had told you guys that I had 2 to the 2 plus 5, well, that means that originally I had 2 squared times 2 to the 5th. That's what we're going to do here because it's being added. What this really means is that originally I had 3 to the x times 3 to the 4th. Because when you multiply things with the same base, you add the exponents. They are being added, so we know this originally came from multiplication. Now I can actually evaluate this. I know 3 to the 4th is 81. Now I have an equivalent expression. These two are equivalent, but x is by itself. So that's really what we are doing here, is we're just using those exponent rules and how they all work together to be able to kind of rewrite these in a sense. So I'm going to do one more example that puts all of this together. We are going to look at the function y equals negative 10 to the 2, times 2 to the x plus 3 plus 5. Before we even rewrite anything, and I know I'm going to have to rewrite it because x isn't alone. Before we even rewrite anything, we can immediately determine if this is growth or decay by looking at my b-value. Because my b-value is greater than 1, I know that this is going to be a growth graph. That tells me immediately that I'm going to go from flat to steep. So on the left-hand side, I'm going to have my horizontal asymptote. On the right-hand side, I'm going to go to either positive or negative infinity. So just by knowing its growth, I automatically know these two things. Now, in order to find anything else, to figure out what my a value really is, I need to rewrite this. So I'm going to say y equals negative 10. We know that these parentheses represent multiplication, so times 2 to the x times 2/3 plus 5. Here, I'm just using my order of operations. The first thing I need to do is my exponent. So that's really 8. So I get y equals negative 10 times 2 to the x times 8 plus 5. Now I can do any multiplication. Well, I know that I can actually do negative 10 and 8. So negative 10 times 8 is negative 80. And now I have an equation in the form of y equals a times b to the x plus k. Therefore, I'm ready to find the rest of my stuff. So now I can find my y-intercept. We know that my initial amount is 80, but it gets shifted up 5, so that becomes negative 75. That's where my y-intercept is going to be. I can find my horizontal asymptote. My horizontal asymptote is at y equals 5. Because of that, I can do kind of a quick sketch. Once again, I know that my a is negative, so it's going to be going down. My asymptote's way, or my y-intercept's way down here, and my asymptote's way up there, but we can kind of put those together. It's going to look something, it's not the best sketch in the world, something kind of like that. That's going to allow me to do my end behavior. For my end behavior, once again, the biggest thing is knowing that on the left-hand side, I'm going towards that asymptote. On the right-hand side, because it's a negative a, I'm going to negative infinity. Because it is a negative graph for my range, I know that I'm starting at negative infinity and I'm going up to that asymptote. And there you have it. That is an overview of some of the basics of the key parts of exponential functions.